Okay, this is our fourth lecture for Unit 2. And this is a longer one. We're going to get into more details related to the definition of minerals. Now, we've sort of covered all of the necessary background related to the atoms of different elements and how we bring those atoms together through atomic bonds. Now that we have the ways to connect the building blocks, we're going to talk about what they ultimately build, which are minerals. Okay, so as a simple definition, minerals are four things. One, they are naturally occurring and inorganic. This essentially means that minerals aren't living. They are inorganic, they're non-living, and they form naturally. They don't form by humans in a lab. They aren't created by humans. They have to form in nature. Second up, they are solid. Minerals are solid. They can have various hardness to them, but they are not liquids and they are not gases. Here's the one that's a little bit more technical. Minerals are repetitive arrangements of atoms with a crystalline structure. So remember, we talked about how atoms can come together through bonds. Those bonds will actually build a crystal structure. And what's interesting about minerals is that that crystal structure will repeat itself in various directions. We see that with this example here, that the mineral is building this crystal structure and it is going out in various directions. But if you compare and look at each of those parts of that quartz mineral are actually identical to each other. They're the same pattern. And so this is that repetitive arrangement of the crystalline structure that is at work. And this is true for all minerals. Even if the mineral doesn't look as clean or as beautiful as the one in this image, at a microscopic level, it is still a repetition of the same arrangement of atoms. And then finally, minerals are formed through crystallization or precipitation from a fluid. So this could look like the crystallization out of a cooling magma chamber, forming a nice, beautiful mineral, or it could look like the formation through a liquid like water. Sometimes minerals can form as those elements are being precipitated out of a solution of water. But in general, we go from a liquid or a fluid and we transition that into the solid crystal structure that we associate with minerals. Okay, so let's talk a little bit more about these different examples. Minerals must form naturally, and there's actually a really wide range for how these can take shape. It doesn't just limit itself to just one place. There are actually biological processes that can create minerals. It doesn't mean that it is not a mineral just because it was created through nature. It does exist that way. It's just that the material can't be living itself. And so an example are shells in the ocean. Organisms build their shells out of the mineral calcite. And this mineral is the arrangement of different calcium, carbon, and oxygen atoms. They are building it completely through nature, through these biological processes, and it is an orderly arranged crystalline structure. They use it for their skeletons or their little homes, but it is still inorganic. It is not living. Here's another example. Many microscopic plankton-like creatures called diatoms build their shells or their casings out of the mineral calcite. And so here's a microscopic view of those diatoms. And there are not just a few of these, there are countless numbers of diatoms that stack one on top of the other to form these massive deposits. And here's an example from the White Cliffs of Dover in the UK. Okay, requirement 2, minerals are solid, not liquid or gas. Minerals will have a solid nature to them, and they can have a variable amount of hardness. They don't necessarily all have to be of the same hardness to be a mineral. And in fact, the hardness of a mineral directly relates to the type of bonds that are connecting its atoms. To measure this, we use the Mohs hardness scale, which is a ranking of different minerals by their increasing level of hardness. Many of you have heard that diamond is the hardest mineral. It is definitely at the top of the scale, so it receives a 10. Everything below the 10 would be capable of being scratched by the diamond. So for example, quartz, if you were to take a diamond and a piece of quartz and scratch them with each other, the diamond would scratch the quartz, not the other way around. If you were to take the quartz though, and go to a piece of calcite similar to the ones that were being made by those marine organisms just a slide or two ago, the quartz itself would be harder than the calcite and would be capable of scratching it. Just for reference, our fingernails have a hardness of about 2.5, and so they can be really helpful for telling the identity or the identification of gypsum or calcite, because sometimes these can actually look very similar to one another. And so you'll get more practice with this in lab, testing out the different characteristics of these various minerals. Here's another example of how the crystal structure inside the mineral really controls the hardness of that mineral. Graphite, which is commonly used in pencils as used for writing, it is made out of carbon. And those carbon atoms are really weakly bonded together through those intermolecular forces that we talked about. Those are the weakest bonds, which makes sense. You use a pencil in order to write on a piece of paper, and so you don't want it to be very hard. Take that same carbon and put it under intense heat and pressure, it will be transformed into a diamond. That diamond is the same carbon atoms. However, they have been bonded together now with covalent bonds. So those strongest bonds that we looked at, now all of those carbon atoms are being bonded together through a covalent bond. And so that mineral now, the diamond, is exceptionally hard. It has a Mohs hardness scale of 10. Okay, number 3, crystalline structure. What does that really mean? Here's a visual example of it. Here are various atoms in this mineral quartz. They are being organized together in an orderly structure. So we would call this the organized crystal structure for this quartz. Quartz is a mineral. It's going to have this orderly crystalline structure. This is sort of just the pattern of how all of the atoms are bonding together. Now, there are some solids out there that lack that crystalline structure. They may even be made out of the same material as the minerals. Take, for example, opal. Opal is made out of the same atoms, same elements as quartz, but this material does not have that orderly structure. We call it, in fact, a glass. It is amorphous. It is disordered. And so opal, even though it is incredibly beautiful, it is not considered a mineral. It is considered a glass. These atoms lack that organized structure. In fact, the reason why we get this beautiful color pattern from the opal is because of light's ability to bounce around inside this amorphous structure. If you've ever seen the movie Uncut Gems, the inside of the opal that is shown in the beginning of the movie. And so I always like to connect that to this part of the lecture. Just a quick another aspect of this, minerals can be made of one element or they can be made of multiple elements. So here are the elements of the periodic table, and some minerals only contain one element inside of them. Take, for example, gold. Native gold has those metallic bonds bringing it together. Here's a really large gold nugget as an example. There is also elements that have multiple elements inside this mineral. Muscovite is an example, and it has potassium, aluminum, silicon, oxygen, and even hydrogen in it, all bonded together in a complex fashion. Okay, fourth requirement. Minerals must crystallize or precipitate from a liquid. This can happen in a lava or in water. And I wanted to show a video to give you a sense of what this looks like over time. This is a solution. This solution has dissolved atoms inside of it. And as the temperature changes in the solution, the minerals will begin to grow along these edges. And those are occurring because different atoms are bonding to the surface of the mineral. The conditions within the fluid are not great for those atoms to remain in the fluid. And so instead, they start to bump up and connect with the edges of the mineral, and the mineral begins to grow outward. I think over here, there's going to be a mineral that starts to grow out in all directions. So it's a cool little seed that gets planted. Again, they're adding ice to the solution in order to force the free atoms that are floating around the solution, to force them to contact and bond with the surface. Here's that new seed that sort of sprouted and began to grow in all directions. Just watch it slowly and it'll grow out in all directions. That edge keeps moving forward. Oh yeah, really big. Cool. Okay. So that was just an example, and here's just an animation or a graphic just sort of showing you that change over time. When crystals grow, they will encounter other crystals over time, and this is where they don't form that perfect pattern, is because they bumped up into each other, or they might have imperfections inside of them that cause them to grow in new directions. Okay, now we're going to shift our attention towards mineral identification. And there are several characteristics that you're going to need to do your lab, and so I wanted to cover those here. There are over 5,500 different minerals that have been identified by the International Mineralogical Association. That's a lot of minerals. That's just a lot. And so you might ask yourself, how do geologists tell the difference between them? Well, there are some clues and some characteristics that help us tell the difference between many of these minerals. And we're going to go over those. So first up is called crystal form. This is the pattern of the mineral that it takes as it grows. It can also be called crystal habit. And so really, when you think of crystal form, think of how the mineral is growing. As it is growing and from a liquid or a solution, it is growing outwards in a certain direction. That is its crystal form. This is different from its cleavage. Its cleavage or its fracture is the way that the mineral breaks. It sounds similar, and it might be hard to look at it and tell the difference, but if a mineral looks broken, it has probably broken that way. And that surface that it is broken on is the cleavage surface. If it lacks a clean surface, it has probably fractured along an irregular surface. And so we would call that fracture. We would not call it cleavage. There's also color. You might have thought that this would be the first one to consider. However, there are lots of minerals that have very similar colors to one another, so it is a very poor indication of the identity of a specific mineral. And then finally, we have luster. Luster also is not super great for identifying minerals. Really, we want to focus on the first two. Luster just refers to how does light reflect off of the surface of the mineral. Is it very shiny or is it very dull or earthy? That is sort of a simple description. So first up, crystal form. This is basically the pattern that the mineral is taking as it grew. We watched that mineral grow in that video just earlier. This vivianite has a very belated pattern to it as it grows. Table salt is also called the mineral halite. This is the combination of sodium and chlorine. And this is bonded in a cubic pattern. All of the atoms in the halite, in the salt, have a 90-degree angle relative to each other. And so it forms a cube. And so this cube pattern lends itself to growing in these cubic-like shapes. Now, cleavage. Cleavage is how the mineral breaks. And breaking a mineral has a lot to do with which bonds are the strongest and which are the weakest. Minerals break along the weakest bonds. So we have a pattern of elements here bonded together. And these red and blue atoms are very tightly bonded together, very strongly bonded. These gray elements, these gray atoms here, have very long bonds between the sheets of red and blue atoms. These very long bonds are much weaker than the tightly compacted short bonds of these red and blue atoms. So if we were to predict where would this mineral break if it were to be stressed or broken, it would probably break along the weakest bonds, which are these gaps in between these very large sheets. So we call this cleavage, that this mineral is sort of breaking off in sheets. It is breaking off along these gray atoms, and it is taking off this entire sheet of red and blue minerals, atoms. It can also, doesn't have to just be sheets, it can be in cubes. So like with halite, there are multiple different angles at which you can cut a mineral and break it. And it can break those bonds because they are equally strong or equally weak in all directions. When we do not have any preferred plane of weakness, any sort of gap or place where the atoms are the weakest, we don't get any nice surfaces from which to break the mineral. And in this case, we get a fracture pattern. This fracture tends to have very irregular surfaces that we cannot see a strong pattern for the breakage. Okay, so those are the 4 different methods for identifying minerals: crystal form, cleavage or fracture, color, and luster. Finally, there are 5 additional tests that can help add a little bit more specificity. There's hardness. We've already talked about this, as how hard is the mineral, how resistant is it to breaking. Effervescence just means, will the mineral dissolve in acid? Streak is, what is the color of the fine-grained material that is scratched against the surface? Sometimes that actually changes color compared to the mineral as a whole. Magnetism is the material magnetic? And then density, how compact is the matter contained within it? Just a little bit more about hardness. Remember, hardness directly relates to the types of bonds that are being used to connect the atoms inside the mineral. The minerals that have the weakest bonds have the lowest score on the Mohs hardness scale. The atoms that have the strongest bonds, those covalent bonds, those are going to have the hardest or the highest number on the Mohs hardness scale. And it doesn't just trend linearly. Let's take, for example, apatite. Apatite is not, or diamond is not twice as hard as apatite. It actually scales exponentially. And apatite is 10 or 20 or 30 times weaker than diamond. Diamond is incredibly hard. It really sort of goes off the charts when we think about just how much strong it is. And remember, here is sort of our trending list from strongest to weakness. Covalent bonds are the strongest. Next are ionic bonds, then the free-flowing metallic bonds, and then finally we have those intermolecular forces. Okay, thanks for sticking with us for that longer lecture.